Hello everyone, in this video we will be discussing the questions of theory of computation and compiler design asked in the year 2013 and 14 of ISRO Scientist Engineer Computer Science paper. Let's move on to the question. Okay, this is the first question. In this question, this is asked in 2013. Okay, we are asked to eliminate left recursion. Okay, and we are given two predictions. Okay, so now let's first see what is left recursion and how we can eliminate it. Okay, if we have a prediction such as A which derives to A alpha, where this A is a non-terminal, okay, and this alpha is a string. So this type of grammar is called a left recursive grammar. Okay, left recursive grammar. And how we can eliminate it, how we would eliminate it. Okay, so now let's see. We have, suppose we would first having some example. Suppose we have A is equal to A alpha, okay, where alpha is a string and beta may be a string or it is a non-terminal. So it is replaced by, this is a left recursive grammar, so this grammar would be replaced by, now let's see how. A implies beta A dash. That is a symbol which is, that is a set of string which is independent of this A. It would be written over here, and A dash implies alpha, that is a that is the string which was with this non-terminal, that is alpha A dash or epsilon. So this would be our grammar. Okay, now let's check here. See, for left recursion, both this A and this both non-terminal should be same. So first grammar, that is S belongs to A and B, it is good. So there is no left recursion here. Okay, so now for the second grammar, so we have equal to AC. Okay, or for in place of this S, we would be substituting AA and B. When substitute A, capital A, small a in the place of S, we would be having capital A, small a, D. And we substitute B, we would be having BD, and we would be having epsilon. Now see how. From this example, we would be comparing it. This is beta, okay, and this AD and this C, this is alpha. So now let's see how I'm writing it. So first I would be writing is A implies beta A dash. So now what is my beta? Beta is BD A dash, or A imply A dash. Okay. Second, A dash implies alpha A dash. So now what is my alpha? Alpha is C A dash or AD A dash or epsilon. So this is my answer. So now let's check what is there. So our option should be B, because in B only we have A dash implies C A dash, AD A dash and epsilon, and A implies BD A dash, and S implies capital A, small a and B. So our answer should be B. Okay, this is our answer. Next. Shift reduce parsing belongs to which class of parsing? Okay, for broader, when we talk about broader concept, we have top down and bottom up parsing. Okay, this is top down and this is bottom up. When we talk about top down parsing, we have recursive descent parsing, which is recursive descent. Okay, DESCENT, recursive descent parsing. Okay, and this recursive descent is backtracking and non-backtracking. So there are two types, backtracking and non-backtracking, and this non-backtracking is predictive parser. Okay, it is predictive parser, and this predictive parser is further called LL parser. Okay, so when we talk about top down, we will be calling it as LL parsers. Now let's see what is bottom up. Bottom up, we have shift reduce parsers. Okay, so shift reduce parser is bottom up, so answer should be A. So now let's see. This shift reduce parser are also called LR parsing, and this LR parsing is further divided into three, that is SLR, LR and LALR. So questions can be asked from any of these types also. So for this, our answer is A. That is, okay, it should be bottom-up parsing. Shift-reduce parsing is bottom-up parsing. Okay. Okay, in the last question, it was bottom-up parsing. I marked it wrong. Okay, shift-reduce parsing is bottom-up parsing. Okay, now let's see. What are the final states of a DFA generated from the following NFA? Okay, we have this NFA. Obviously, it is a NFA. Okay, so what are the final state of DFA which is generated from the following NFA? So see, now what is this? Epsilon closure of, we have to calculate the epsilon closure of each state. Okay, so epsilon closure of Q0 would be Q1 and Q2, because from epsilon move from Q0 we can go to Q1 and from Q1 we can go to Q2. So epsilon closure of Q0 is Q1, Q2. Okay, so the epsilon closure of a state which contains a final state. So epsilon closure of Q0 contains Q1 and Q2, in which Q2 is the final state. So if the epsilon closure of a state contains a final state, then this state is also final. So Q0 is made final. Okay, so let's see for Q1. Okay, so epsilon closure of Q1 is Q2. Q1 and Q2 is the epsilon closure of Q1. Okay, so if the epsilon closure of Q1 contains the final state, that Q1 is also final state. So here the answer would be Q0, Q1 and Q2, which is A. A should be answer. Okay, next question. The number of states required by a finite state machine to stimulate the behavior of computer with memory capable of storing M words. So here we have M words. Okay, sorry. Okay. Here we have M words. Okay, and each word is of N bit. So total number of bit would be M cross N. Okay, this would be the total number of bits, and separate state for each bit combination. There would be, so this is the total number of bits, and there would be a separate state for each bit combination. So it would be equal to 2 to the power M cross N. So now this is the answer, 2 to the power M cross N. Now let's take an example and explain. Suppose we have 4 words. Suppose we have 3 words, W1, W2 and W3, and each word is of 2 bit. Okay, let's say 00, 01, 00, 00 and 00. So for this 2 bit we can have 4 combinations. So it would be 01, 10 and 11. Similarly, it would be 01, 10 and 11. It would be 01, 10 and 11. Okay, now let's see how. See, for this word, for this, the first 00 combination of the word 1, it can be combined with this, this, this and this. That is 4 times. Okay, and for also this 0 can be combined with this, this, this and this. Okay, so there would be around 2 to the power 2 plus 2 into 2 when we compare all of them. So it would be equal to 2 to the power 6, which would be equal to 2 to the power 3 cross 2. So the answer is M cross N. Okay, next question. So what is the number of steps required to derive the string this from the following grammar? Okay, we have a grammar. We have to see the number of steps. So let's start. First we would be doing for the outermost one. So for the outermost one, we would be using we will be using this production. That is this one. This production. Okay. So I will be writing the production which I have used here. Okay, I have used this production. Okay, now next would be, it would be SS. So here we have used the production SS, SS. Okay, next S, S. So here I would be using the production S belongs to this. Okay, now we would be expanding the other one. So we would be substituting this S with epsilon. So it would be S like this. So this is S it derives epsilon. Okay, so till now we have computed this much, so this is remaining. So in place of s we want this. Okay, so now let's go on to the next step. So we have s, this and this, and here in place of s I have written this one. Okay, now furthermore in place of single s I would be writing double s. Okay, so this is like this. So s I have used this production. Okay, so now I would be doing s, see, one s I have substituted. Okay, so this, so it is like one s I have replaced with this. Okay, so I would be expanding that s, and here the second s also I would be substituting. Okay, so this is s. Okay, I have done this only. And okay, actually this only. Okay, next I will be substituting epsilon for both the s's. So first epsilon I will be keeping it like this only, and second epsilon. Okay, so for both these production it is s derive epsilon. So how many steps? 1 2 3 4 5 6 7 8 9 10. 10 steps are used, so answer should be A. 10 is the answer. Next, how many states are in a minimum state deterministic finite automata accepting the language? So we have to accept this language. The number of 0 is divisible by 2. Okay, and the number of 1 is divisible by 5. So it can be that is 0 by 2. 0 is divisible by 2 and number of 1 is divisible by 5. So by Myhill, you should learn this theorem also. By Myhill-Nerode theorem, you can conclude it like it would be around 2 into 5 states, that is 10 states. So answer would be 10. So let's draw a DFA for this also. So I'll draw a DFA. So I have to, first it is number of 1s divisible by 5. So I would be requiring 5 states, 4 states actually. So it is Q1, Q2 it takes 1. Okay, Q3 it takes 1, it reaches Q4. Okay, then we have Q5. So we have 5 ones, 1, 2, 3, 4. On the 5th one, I wanted to return to Q1 only. Okay, divisible by 5 means it would be 0, 5, 10. Okay, so at 0 also it would accept. When number of 1 is 0 also it should accept. So this I have made for 1. So now let's make for 0 also. So in this I would be writing it as Q6, Q7. So here also I will be writing it as 1. I will be writing Q8 it as 1. Q9 we are writing 1. It is Q10. So we have used 10 states, and on returning 1 it would go over here. Okay, so see, we are making a DFA. So on 1 it is here, and for 0 it is here. For 1 it is here, for 0 it is here. See, when I traverse 0, that is 0, 0. That is 0 is divisible by 2. That is 0 times 2 times 4, 6, 8 and so on. Okay, so like in the same way, I would be writing it as, okay, wait, I would be writing it as, it would be like 0 here and 0 here. It is same over here, 0 here and 0 here. 0 here and 0 here. 0 here and 0 here. So this is our DFA. It would contain 10 states. So answer is C, 10. Okay, next question. The following finite automata recognize which of the following languages? Okay, so we have a automata and we have to see it recognize which of the following languages. So we would be going from the options. Okay, so from the options, from this option, the smallest string from this option can be, this is OR, 1 or 0. Okay, so it is a asterisk. So it is 0 times 1 or 0. The smallest string from A is 0, 1. Smallest string from B is 1 because it is an asterisk over this. So it can be there, it cannot be there. So is 1. Smallest string from C is, so asterisk is for 1 or 0 only. So 1 and 1. So smallest string for C is 1, 1. And smallest string for D is, so let's see. For A, 0, 1 is it acceptable? Yes, 0 and 1 it would accept. 0 and 1, yes, it would accept. Okay, so for now my A option is there in my options. For B, would it accept 1? No, it won't accept 1. 0 has to be there. So B is not in my option. C, 1, 1. 1, would it accept 1? No, 0 has to be there. So C would not be there. Okay, now let's see for D. So it is like here, it is like 1 asterisk. So it can be 1, it cannot, there cannot be 1. 0 asterisk, 0 can be there, 0 cannot be there. Either 0 or 1. So if it is 0, so then also it is not acceptable. If it is 1, then also it is not acceptable. So D is also not right. So option is A. Okay, so next question. Consider the following grammar. So we have the grammar. Which of the following statement is false? So we have to prove which of the following statement in this grammar is false. So now let's see. The length of every string produced by grammar is even. So let's check. If I have S is equal to AB. So if I replace A, it can be this. S is equal to SAB. If I replace A, it can be BABB. Okay. If I replace B, it would be BBA. Okay. And if I replace this B, it would be BBA, BBA. Sorry, it is capital A. BB capital A. And in place of capital A, I'll place small a. So it would be BBAA, BBA, BBA. So it is even number strings. Here also if I substitute, it would be even. So first one is true. No string produced by this grammar has 3 consecutive A's. Okay, here also see we don't have 3 consecutive A's. We have 2 A's, 1 A's, but we don't have 3 consecutive A's. So this is also true. The length of the substring produced by B is always odd. Let's see if we have BBA. Okay, so this A can be substituted by BB small a or BB capital B AB. Okay, so it would always be odd only, because here also it is 3, here also it would be always be odd only. So C is also true. No string produced by the grammar has 4 consecutive B's. So now let's see if the string produced by the grammar have consecutive B's or not. So I have, suppose we have S is AB. Okay, so in place of A I have written A, B is same. So I have changed this B. Now I would be changing this B. It is A, B, B, A. Now I will be changing this A. We have A, B, B. In place of this A, I would be writing capital B, small a, capital B. Okay, so I would be substituting both these B's. That is A, B, B. In place of B, I would be writing B, B, A. See, I have 4 consecutive B's. Okay, so this one is false. So answer should be D. Okay, next. Which of the following is false with respect to possible outcomes of a Turing machine executing over input? Okay, so when a Turing machine is executive, there are 3 possible outcomes. The first one, it may halt and accept input. Okay, the second output is halt and reject input, and the third outcome is it may never halt. Okay, so these 3 are the outcomes of a Turing machine, but it may not change. This is false. So B is the answer. Okay, next question. Consider the following deterministic finite automaton. Okay, let SS denote the set of 8-bit strings. Okay, set of 8-bit string. So I have 1, 2, 3, 4, 5, 6, 7, 8-bit string whose second, third, okay, 6th and 7th. 6th and 7th bits are ones. Okay, so here it can be either 0 or 1, here it can be either 0 or 1, here it can be either 0 or 1, or here it can be either 0 or 1. But the second, third, 6th and 7th bit are 1, and the numbers which have these bits as 1 should be accepted by this automata. Now let's see. Okay, a first bit, see here the first bit, if the second bit needs to be 1, so second bit should be here, this one should be the second bit. The first bit should always be 0, then only the second bit be 1. The first bit would be 0. Okay, so it is 0, 0, second bit is 1, okay, it is possible. Okay, third bit has to be 1, second bit is 1, second and third bit has to be 1, 1. Okay, if the second and third bits are 1, the fourth bit, it has to be 1 only. So fourth bit would be 1. If the fourth bit is 1, fifth bit can only be 0. Okay, fifth bit can only be 0. And the sixth bit, it has to be 1 because it is a compulsion. It is given in the question. So sixth bit, it has to be 1. Okay, and the seventh bit, sixth bit has to be 1, and the seventh bit, it also has to be 1. Seventh bit, it also has to be 1, and the eighth bit, it can be either 0 or 1. So how many numbers are possible? 0, 1, 1, 1, 0, 1, 1, 1, and 0, 1, 1, 1, 0, 1, 1, 0. 22 numbers are possible. So answer should be 2. So this is the answer. So this was all about the question paper of 2000 till 2013. So please stay tuned. If you like the video, please click the like button. Please do subscribe. If there is any discrepancy in this video, please feel free to comment. Thank you.